The normal distribution. That should be over there. The normal distribution. This is the bean machine. Thank you, Albert. And you pretty much drop a little ball at the top, and it bounces around between all the little pegs, so it gets random motion in there. And it ends up falling into one of the slots. So there's an average. Right? They kind of fall in the center a lot. It's the most likely. But there's other possibilities, and they kind of spread out. The less likely it goes. But in the very center is the most likely. They call it the normal distribution. I like what Dr. Math said. You know, my subject of Googling. So I don't know who it is, but I like what he said. He said, could be a she, I guess, right? When many factors contribute to an outcome, and each factor contributes in the same way, then it does not matter how the factors are distributed. The net result will be a normal distribution. So that's kind of where we're taking a look at here. Here's an example. And I tried to get this to work, but the balance won't turn on, so I made up the numbers. But it's around. I can't be that far off, right? So it's just a whole bunch of pencils, and masked each one, started writing down all the numbers, right? They should be identical, because they go through a lot of work to make these identical. So it should probably follow a normal distribution. What would also follow a normal distribution is just taking this one pencil, right, and massing it. Now you'd probably want to get a really good balance so you can get some, get some resolution here, get some numbers to bounce around with the error. But you could also get a normal distribution just by measuring one pencil. Okay. So what we're talking about is measuring results of some experiment and trying to get the same thing over and over and over and over, right? But it's very, very applicable. Think of Dasani's bottled water. The same bottle over and over and over and, right? That's what they want. They don't want any variation in there at all. iPads, whatever. Pretty much every single commercial product is this. The normal distribution it's going to follow. And if you are the manufacturer of Dasani, you're going to have a lot of questions. If you're the manufacturer of the pencil company, you can ask a lot of questions. What's the probability of getting a result bigger than, right, the Dasani bottle? What's the probability of getting a volume lower than, right, because no one's going to want to buy that one? You have a manufacturing process going on, making the same thing over and over and over and over again, but there's a normal distribution of results. So what's the probability that you're going to make a sucky bottle? What's the probability that, the pencil's messed up, or there's a difference? What's the probability of getting a result less than or bigger than? Or what is the probability of getting a result between two possibilities, right? Now, I don't know, let's just make something up. Kids are jamming these things up their nose. And it's the 6-year-old nostril that is exactly a range of sizes. And this eraser, when it is between these two sizes, jams up there, and you're going to get sued because you know everything there is about it, right? So what's the probability that your pencils are between these two numbers? If it's somewhat significant, the lawyers say, we can't afford it, or we can, you have to make some major changes. So there's a lot of questions you can ask about the normal distribution. Today we're going to find out how to answer the questions, okay? But we need to start with the histogram. So what are the axis labels on a histogram, right? Jesus, where does the measurement go? Right? The Dasani bottle, or whatever the measurement is. And then you have tally. That's really what a histogram is. You're just telling stuff up. You're saying this result, oh, okay, I got it 10 times. And then you, right at the tally of 10, you make a little dot. Tally and measurements, where would they go? If you're going to make a histogram. Tally. Tally is up here, right? That's the convention. You've heard of tally before, right? Like, oh, it showed up 10 times. Your tally is 10, right? The measurement down here, or the result, whatever it is. Usually it's a measurement. You know, what's the probability of getting that measurement? So it's a measurement, right? How many times did that measurement show up? That's the tally. Assume a histogram of results is created using an infinite number of measurements. Infinite number of measurements. It's going to take forever. It's theoretical. This histogram contains blank of the possible results. Victoria. Most? All? Has to be all, right? You did it forever. That's contain all the possible results. Sketch the obtained distribution on the above plot for such a histogram. Okay? And label the locations of the standard deviation and average. Okay, well first, just like the beam machine, you're going to have a normal distribution has some peak, some center, right? And then it just kind of, it's symmetric on both sides and kind of curvy looking. So if your art's better than mine, like mine doesn't even look symmetric, it looks lopsided, right? So that would, all right, no, just pretend. Pretend you see this nice, beautiful, symmetric curve with the peak, okay? You can't see a lopside. That's not a normal distribution. There's something going on there. Okay, so it's nice and beautiful and symmetric. Where would the average be, Zach?
The average would be at the center of the normal.
Center. Right here. Now, when I say average, you got to read the measurement at the center. That's the average. The measurement. Not the peak. We're not talking about this dot right here. No. We're talking about what is the measurement at the center. How would you describe the standard deviation, Mariella? How would you describe the standard deviation? One way of thinking of spread of deviation is the spread of the measurements. Maybe you've heard that. Okay, it's some width. Now, where is that width going to be? It's exactly where? Maybe you've heard of FWH. If you've taken statistics, but I don't know. Full width, half max. You go up exactly halfway. Go up exactly halfway. I don't know. Again, you probably need a ruler or something. Right there. Oh, what's the symbol for average? X with a line over it. Okay. However, and standard deviation? S. Okay. However, we just said we did an infinite number of measurements. X bar is what you get in the lab. 10 times, calculate an average. That's X bar. For a population containing all possible measurements, it's not X bar. The symbol was in the reading. It's Greek. Mu. Mu. So this is for a population where you know all possibilities. For us, we're never going to do that, so we're never going to use mu, right? We're always going to use X bar. But how about standard deviation in the book? Another Greek symbol. Yeah, what do you call that? Sigma? But we're never going to use mu or sigma because we're not going to do it an infinite number of times, right? Okay. Bless you. When getting a result, the probability of getting a result that exactly matches one in the distribution, Brandy, is, so in this plot we have up here, we did an infinite number of times. We're going to make a measurement. The probability of getting exactly one of these measurements is 100%. They're all there. All your choices are there. Okay. So let's clean this up a little bit. Select a range of measurements. Let's see. Well, that's good enough, I guess. Select a range of measurements in the above distribution and shade in the area under the curve that corresponds to the selected range. I don't care. Okay, we'll go to... Doesn't really matter what you shade in, right? I'm just going to pick this. Doesn't really matter. Okay, I'm shading that in. What does the shaded region represent? What does it represent? It represents the probability of getting a measurement between what two measurements? Yeah, my borders. Yeah, I guess you can call them x1 and x2 or something maybe, right? x1. Clean this up so you can read it. x1, x2. So the shaded region is the probability of getting a measurement between x1 and x2. That's what the shaded part means. Okay. If the entire curve was shaded, Sochi, if the entire area under the curve was shaded, it would correspond to what percent? What did she say? Anybody help her? 100. Yeah, it's all possibilities, all measurements. Okay. Make sense so far? We're good? Okay. So in order to determine probabilities for ranges of results, plotting histograms of all possible results and shading it's ludicrous. You can't do it, right? So instead, when it comes to normal distributions, we're going to replace the x-axis with the z-axis, where z is defined as, I got to look down here and cheat, because I always forget what it is. Okay? Your measurement minus the average, all of their standard deviation. Now when I cheated, I was looking down here. But notice that's for population. So I just replaced mu with the average and sigma with, oh, I didn't replace my sigma with my s. Right? Okay. Then the histogram would look like, so we're just changing the x-axis. This is now z. I mean, it's not going to change its shape. But now this center is what number? What is that center right now? At that center, x was what previously? At that center, x was the average. So x is the average. If you put in to this equation, if you put in this equation for x, put in x bar, what do you get? X bar minus x bar all over s, which is 0. This is z equals 0, right in the middle. Okay? So the question really becomes, how the heck does this particular change in axis give probabilities for different ranges of measurements? Answer all those questions we asked before. Bigger than this measurement, lower than this measurement, between these two measurements. What's the probability? That was the trick. It's a little more complicated. You need a table. Someone did a lot of calculations for you on the normal distribution and getting areas. Okay? So let's pretty much, I'll just jump ahead a little bit here. Let's say you pick z is 0.1. Just pick z equals 0.1. Okay? So you look in the table, find z is 0.1. The area is 0.0398. Area is probability, remember? Because you said that you shade the whole thing, that's 100%. Shade half of it, that's 50%. So these are areas. But to get into percent, probably multiply it by 100. So at z equals 0.1, that corresponds to, what is that? About 4%, 3.98%. Well, 3.98% to do what? To fall between z equals 0 and z equals what? 0.1. That's what they did. They calculated these areas for us. It's pretty much just integration, right? So that's how this table works. Z represents the area or the probability between z equals 0 and z equals that number in here. Okay, so that's the game we're playing.
I have a question.
Yep.
So we're looking at absolute value of z, a.
Now, well, hang on. Why do they have absolute value? Why don't they have a whole nother table with the negative z's? I cut you off a little bit, but we'll get you there. Why do they not have another table with all the negative z's? Because the plot normal distributions are symmetric. You don't care. All right? From z equals 0 to negative 0.1, which is something somebody could be very interested in, right? Lower than the average instead of bigger than the average. Yeah, what's the same dang table? Okay, what's your question, Seth?
Why is the z value of 0.0.3989?
Good question. We're going to get to that to the very end of the hour. Okay. So, but let's learn how to use this table. Sketch. This is the Smith plan here. Everyone's going to like it but Eric. So Eric, you just got to suck it up. Okay. What is the probability a measurement will be greater than the average? Okay. It's going to be a lot easier if you just sketch these first. So, sketch the distribution. Where is the average? Right in the middle, right? And you can even add more detail there, z equals 0. But greater than the average, what side do I shade? Yeah, and shade it all in, right? Now this is overly making this more complicated than it needs to be, but it's really going to help us when things get more complicated. So the probability is 50%. Half the area is shaded. That's all you're after. You're after the amount of area that's shaded. What is the probability a measurement will be between z equals 2 and z equals 0? So on your graph, you find z equals 0. The graph, you find z equals 2. All right. Shade it in. All right. The answer would be what? Where is it? I can't find it. Z equals 2. Now, you're trying to find the area. I guess I could finish this thing in if I wanted, right? You're trying to find the area between z equals 0 and z equals 2. How can you get that number? You're supposed to use the chart. But doesn't this perfectly match the definition of z equals 2? Because at z equals 2, that's the area between what and what? 2 and 0. That's how z is defined. So all you got to do is look in the table, find z equals what? 2, and get your answer. Where is it? Oh, here it is. Right here. So the answer would be what percent? 48%. Well, yeah, 47.73. I wouldn't say 48. There's a lot of 48s in there. 47.73%. Okay. And it's just going to get more complicated as we go on here. So ask if I lost you. Make sense? Andrew, you see what I'm doing? Okay. What is the probability that this measurement now will be between z equals 1.5 and z equals negative 1? Okay. I guess we should sketch our whole thing in here. We want a negative 1, so that's going to be over here somewhere. And we want a 1.5. That's got to be over here somewhere. (1.5) and negative 1. Alyssa, what's the game plan to figure this one out? Subtract them? Subtract them? Or what? There's not a negative 1, but what we want to find is this complete area. There is no negative area, right? So if we could find, if you could actually put in, let me give you a guide here. If you could plug in z equals 0, right? Between z equals 0 and z equals 1.5, that area would find it in the table. Look up z equals 1.5. The area between z equals 0 and z equals -1, find it under z equals 1. So don't subtract them. We want to add them.
Subtract them 1.5 minus -1 is 2.5, which is what you're looking for, right?
We're looking at areas. This z equals 0 to z equals 1.5, that's,
It ends up being like
we can call it the orange area. That number, that area is what? Where's 1.5? Yeah, 0.4332. The other area, wrong color. This area corresponds to point what? 3413. So add those up, you get 0.7745. Okay, but we like percents, so let's call it 77.45. Okay. Now, before we go on and do something a little more complicated, where's the measurement? These are z's. They're not measurements. I want to know 12.8, not z. You calculate your z, right? I want to know if what's the probability of getting a pencil mass bigger than 12.819. I didn't even say z. I said my x. No big deal. You just go calculate your z, right? Put in that x number that you're interested in. Subtract it from the average of all your measurements. Divide it by the standard deviation of all your measurements, and you'll get your z. Now, what are the odds that that z you get ends up being right on this table? It ain't going to happen, right? I mean, you're going to be really, really lucky if it does. So I think that's the next question. Let's see. Oh, no, it's not. These are still on the table, aren't they? I kind of jumped ahead a little bit. So we're still doing good. What the probability measurement will be between 1.7 and 2? So we haven't got off the table yet. So plug in 1.7, plug in a 2, right, this area. All right, we can put in a 0 if you want. That might help. You need a game plan for that. Monica, you have a game plan for this one? Yeah.
And then subtract the area of 1.7 and 0.
Did you hear what she said? That's exactly the logic that you got to be following. She said, find the area between z equals 0 to 2. Subtract out the area from z equals 0 to 1.7, and you'll have it. Exactly right. So do that. Look up the z equals 2 and subtract out the area for z equals 1.7. Calculators don't even work in this dark light, do they? Right. I don't even have a calculator. Anybody get an answer? 2.19%, I hear. Is that okay? Everybody agree? Excellent. Okay. Now we're more into something more likely that's, right? What is the probability of measurement will be between 1.78 and 2.09? We'll draw it, but how do you get these numbers? Well, yeah, they plugged in, they calculated those z's. They're interested in two particular measurements. You can go back and calculate what those measurements are, right? Just put it into our equation. Right? Put it into our equation here. Put in the z, put in the average, put in the standard deviation. You can calculate what the x was. You can work backwards. Okay. But let's see how we do this. 1.7, yes?
For this, do we round it?
I don't know if they round. You can do all rounding at the end, right?
But, I mean, like, as far as getting the values, it's only to one sig fig.
Yeah, I mean, we probably did kind of exaggerate things a little bit. We probably should say 2%. That would look better. Since we were just talking about sig figs, we should probably be a little more sensitive to that. Thank you, Monica. Okay, what is the probability of measurement will be between 1.78 and 2.09? Okay, let's sketch this one in. 2.09, 1.78.
I think what she was asking was, do you round the z values to match a z value on that table? Because like you said, you're not going to find it out.
You do all rounding at the very end. All rounding is done at the very end. So you calculate your final answer, then do rounding, right? Does that make sense?
Well, no, because, like, for the actual chart, it's not 2.0, but it's the extra 9, so would you use 2.0?
Oh, yeah, this is what we're going to do now, right now. You're talking about this question. Yeah, we're not there yet. This is what we're doing right now. You cannot cheat. You cannot guess and say that's 2. We have to do the I word, and everyone hates the I word. What is the I word? Man, you hate this word so bad you blocked it out. Interpolate. You have to interpolate. We should have been interpolating since general chemistry. The temperature in the lab's 25.5. Oh, that's 26. Right? No, you're supposed to be interpolating this stuff to get the exact number. Okay? So how do you interpolate? We're going to follow a little simple equation here to help you remember it. So that's what we're after. We're after the probability. I think it's easiest to remember it this way. Probability of, sorry, not probability. Well, it's the same thing. Let's call it area, though, because it's directly from the table. Area of the known interval times the fraction of the known interval. Okay, let's show you what I mean here. Okay. The area of the known interval. Okay. Well, we don't know, like Monica said, we don't know 2.09. But in that table, if you go a little bit further, you would get what z number? Z equals 2.1. Right? That's the next, that's in the table. Right? Okay. That's supposed to be a 1.78, right? 1.78 is not in the table. If the next closest z is actually 1.8, right? But then you see how we're going to be losing area? We're going to lose our answer. We have to go not to 1.8, but go to 1.7. Now you see how sketching these things out is really going to help you. So we know, here's our known interval. Z equals 2.1 and z equals 1.7. If the question was, hey, what's the area, what's the probability of falling between 1.7 and 2.1, right? Well, it's easy, right? How would we get that area of that known interval? Look at the table for 2.1 and then do what? Subtract it from 1.7. So do that. Let's find that. The area for 2.1 is 0.4821. 0.4821 minus, I should write that down so we don't lose, so you see where stuff is coming from. 0.4821 minus 1.7, here it is, 0.4554. Okay, that's the area of our known interval. It's too big. So we have to multiply it by the fraction. Okay, the fraction of the known interval. Now this known interval distance is just 2.1 minus 1.7, right? Isn't that the total length? Well, that's all we're really going to do is mathematically find this length and divide it by that length. So 2.1 over 1.7 is the known. That's the complete length, right? Because we want to know what fraction of that length. The numerator would be what minus what? 2.09 minus 1.78. Perfect. And that is our answer. Okay. All right, down all these digits, right? It's way too many. Okay. See if that makes sense. The whole idea of sig figs, this is a really good example of how even if we wanted to do sig figs, we would have to derive a relationship. And the book's not allowing us to. And we don't want to anyway. So for sig figs now, it's almost like, do you remember in general chemistry, day whatever, okay, sig figs, ooh, and then 2 days later, huh? We don't even care anymore. So that's almost where we're at now, because propagating that sig figs through this requires a lot. So we're not even worried about it anymore. Okay. Pretty much give the same number of digits as where you started up, and you're close enough. Okay? Like 2 or 2.1. Now what I want to point out here too is going from here to my answer, this should be one step. We spent a whole lab day on and work using that calculator. This should be one step in your calculator. If it's not, man, make it one step. Your life is going to be so much better. Okay? Okay. What is the probability a measurement will be greater than 1.587? Okay. So I've got 1.587. Here's z equals 0. I have my. All right. So what would I shade in? Everything to the right of that 1.587. .587 definitely isn't in the table, so we know we're going to have to interpolate. But interpolate between what and what? Okay. We need. And it's not even in the table. So what we have to do is we have to interpolate between 1.587 and 0. We need to get the area in green or something. Let's get the area in green. And then do what? Subtract from 0.5. Get the area in green, then subtract from 0.5. All right? So interpolate first between, so I guess you could call this step 1. Interpolate between 1.587 equals z and 0 equals z. Interpolate between those two. And then you'd have step 2, subtract from 0.5. And then you'll get it. Okay? Well, let's do the step 1. So our probability area of the, oh, let's make a little sketch. I think life is easier if you make a little sketch. I've got 1.5, 1.587. Yep.
Why did you put 0.5?
Because I'm only talking about half. Right? The area of that whole half between z equals 0 to infinity is 0.5. So if I subtract out the green part, I'll have my answer. Make sense? Okay, so I'm just interpolating between 1.587 and z equals 0.
What do you mean when you say z to infinity is 0.5?
Because the area under the whole curve is what?
Oh, okay,
The whole area of the whole curve is 1, so half the curve has to be a half. Right? Okay, but ask those questions. So step 1, the probability, that the area of the known interval. Okay? Well, what number am I going to pick here? Am I going to pick a z that's to the left or to the right of the 1.587? Right? If I go over here, I'm too short. What area am I interested in? I'm interested in this area right here, right? So I have to go to z equals 1.6. I have to go to that. I have to. So I'm going to go to z equals 1.6. So the area of the known interval would just be between z equals 1.6 and z equals 0. Well, that's just going to be the area for z equals 1.6, which is 0.4452. Times the fraction of the known interval. So here's, right, here you see that here's the known interval, here's the fraction that I want. You see it? So the known interval, the denominator, is going to be just 1.6 minus 0. The top is going to be this length, 1.8587 minus 0. All right, here's the entire length. There's the top. So get your answer, subtract from 0.5, and you'll have it. So I think you can finish. Well, let's just finish it quick, right? And it'll be complete. 0.4452. So about 44%. Okay. So that's another one that you can do, but it's the same thing. Just realize you can pretty much drop the negatives and do the same thing for number 7.
But after you get your...
Oh, we didn't subtract from a half. Thank you, Andrew. We didn't subtract from a half, so the answer is 6. So this is going to be 44, or 0.44. So the final answer, thank you, sir, 0.5 minus 0.44. 6%. Sounds a lot better. Okay, this is kind of what Zach was asking about. Use table 4-1 to state what fraction of a Gaussian population lies within the following intervals. So what they're saying is that plus or minus 1 sigma, or 1 standard deviation. And if you look at the equation, if you have 1 standard deviation, right, you want that difference to be 1 standard deviation. You want x minus x bar to be 1 standard deviation. Well, that's s over s, or sigma over sigma, whichever population you're looking at. It's just 1. So what they want to get across in this is saying for each standard deviation, that's z equals 1. So if you say z equals 1, you're 1 standard deviation away from the mean. If z equals 2, you're 2 standard deviations away from the mean. So pretty much all you're talking about here, right? Make your sketch. Here's my 0. Plus or minus 1 standard deviation. So z equals 1 on this side, and z is a negative 1 on that side. That's what you want to find the area of. Okay. That's what you want to find the area of. So you look up z equals 1 and pretty much just multiply it by 2. I don't know if that was the answer to the exact question or not. But if z equals, for b, same thing, except now you go from -2 to 2. Sigma, well, yeah, here, remember, they're talking about population. So whether you're talking about x bar, usually we're talking about x bar plus or minus s. Here they're talking about the entire normal distribution. Regardless, it doesn't really matter because we're stuck using that table, whether you have an entire distribution or you have your own set of data. And then there's one last question here. I can get you started on it. This is exactly the same as what we did before, except you just have to calculate your z. Right? What's the probability of having a lifetime greater than 1,000 hours? You just have to calculate your z. Z is x minus x bar all over s. Right? So this is my x, isn't it? Greater than 1,000 hours. Plug that in for your x. That 1,000 has to go in for your x. Somewhere has to be the average. You just got to dig for it. Somewhere is the standard deviation. You just got to dig for it and calculate your z. And then you find the area, right? Whatever that z number is, it's going to be this.
But wouldn't that x value be all numbers that are greater than 1,000?
Yes. So it's going to be all z's greater than 1,000. All z's greater than, you got to calculate it. Put in 1,000 for x. Average is, there it is. You see the top, 845.2. Here's my average. And there's my standard deviation. So you plug in those numbers, you're going to get a z. Whatever z you get, you put it in right here. And that's the area you have to interpolate. And same thing down here for b. Just calculate that z and calculate that z. And I'm sure you're going to be interpolating again. Okay. So you've got some stuff to work on. Review this presentation. You can fast forward over it. It might be helpful. Come by and ask some questions.